Hi. In this next lecture on networks, what we want to do is we want to talk about the logic through which networks form. And by that I mean we want to think of these nodes as being agents in a way. And these nodes make decisions about what other nodes to connect to. And as they make those decisions, that's going to result in a structure to the network. So we're just going to see how that process works and how we go really from the micro level actions of the nodes in terms of making these connections to macro level properties of the network. So the network structure is going to be something that emerges through these micro level interactions. We're going to focus on three very simple ways in which networks might form. The first one's just going to be random connections, where each node randomly decides to connect to other nodes. The second one is going to be a small worlds model, and this is going to work as follows. Each person is going to have some friends that are sort of belong to a clique, that are sort of nearby, and then some friends that are random, that they randomly connect to. So we're going to start out by having people connected to just people near them, and then assume that they sort of rewire in a way and randomly connect to some people who are further away in social space, because this is what a lot of social networks look like. And the last thing we're going to do is we're going to look at something called a preferential attachment network. And this has been used to describe the internet and the World Wide Web. And the idea here is the following, is that you're more likely to connect to nodes that are more connected. So that's true certainly on the World Wide Web. For example, more of us are more likely to put links into Google or links into major universities because they're more connected than we are to link to less connected things. And we'll see how that micro level rule results in properties of the network globally structured in terms of measures that might not have been anticipated. Okay, so let's get started. Random networks. Here's what you do. You just assume there's n nodes, and p is the probability that you connect to another node. So what you do is you draw a bunch of nodes like this, and then with just some probability, you draw connections between the nodes randomly, and you get some sort of random graph. Now this has been studied. There's sometimes called Erdős-Rényi networks. These have been studied in great detail, and here's a really interesting result. It turns out you get a contextual tipping point. For a large n, so that means you've got a large number of nodes, the network almost always becomes connected if p, the probability of being connected, is bigger than 1 over n minus 1. So what you can get is, here's our graph, here's the probability of being connected, which is one of the measures we care about, and here's 1 over n minus 1. And what you get is you get a graph that looks like this. You get a tip. So if you're less than 1 over n minus 1 for large n, odds are you're not connected. And once you get bigger than 1 over n minus 1, odds are you are fully connected. So it's cool, a tipping point within networks. Now these random graphs, you can prove a lot of nice results about random graphs, but the thing is, that's not what real social networks look like. Remember, here's that middle school graph from James Moody. That doesn't look random. Here's the adult network graph from the Framingham study. That doesn't look really random either. And here's an email network. That doesn't look random either. So what we'd like to do is have a network that looks more like what real networks look like. And this leads to the small world graph idea. And this is due to Duncan Watts, who's a network theorist, and Steve Strogatz. So here's the idea behind a small world network. You've got a percentage of friends who are local, who are near you, sort of clique friends. And then you've got other friends who are more random. So your local or clique friends would be the people you work with, the people you live nearby, that sort of things. And your random friends are the people you went to summer camp with, or your old college roommate, things like that. So if you look at real-world social networks, they've got these sort of cliques of people that interact, and then each person has sort of a random friend someplace else, and those random friends also belong to cliques a little bit. So let's look at that network and see how it works. So we're going to open a net logo model here, and what we can do is we can set this thing up, and we're just going to put people in a circle. Now the thing to notice is that in this circle, each person is just connected to people on either side. And there's 40 nodes. And what I can do is I can start rewiring people one at a time so that they've got more and more random rewired nodes. And then what I can do is I can ask, what's happening to the graph? Now notice here on the graph you see clustering coefficient, and over here you see average path length. In this graph you see up here on the upper left, the green line shows the clustering coefficient, and the red line shows average path length. So as I rewire, what you can see is that average path length is falling, but the clustering coefficient is also falling. So let's do this one more time. I'm going to sit here and I'm going to rewire. Notice the clustering coefficient starts out at 1/2, and the average path length is 5.4. Now as I start rewiring, the clustering coefficient falls, and that's because before everybody was connected just to their neighbors around them, so there were lots of clusters. So the clustering coefficient falls, and the average path length is falling fast. It's now down to 2.8, 2.7, and so on. So again, we see this every time we run this. We see a decrease in the clustering coefficient and a decrease in the average path length as we construct this small world network. So what we get is, as people have more random friends, we get less clustering, and we also get a shorter average distance between people. So that's the small world model, and we'll come back to that a little bit in the next lecture, because the small world model, small worlds network, actually tells us a lot about social systems, and it can help us explain the 6 degrees of separation property that I talked about in the first lecture. Now let's go to our third way that nodes can connect to other nodes, and this is called preferential attachment. In preferential attachment, nodes arrive on the scene, and then they've got to decide, who do I connect to? So think of yourself moving into a new city, or think of you creating a web page. So your web page is your node. Now you've got to decide, what other web pages do I connect to? We're going to assume that the probability you connect to an existing node is proportional to the number of connections it already has. So here's an example. Here's a network, and some new node comes in, and it's trying to think about what's the likelihood I should connect each one of these nodes. Well, this node only has one network connection, one edge. This one has 4. And so what's going to happen is when this node comes in, it's going to be 4 times as likely to connect to here as it is to over here. So the probability of connecting to someone is proportional to the number of nodes it already has. Let's look at a NetLogo model of preferential attachment. Now I'm going to set this up, and what's going to happen is I'm going to let this go once. I'm just going to add one node at a time for a second. And what you're seeing here on these different graphs, the top graph is showing you the degree distribution. So there's one node, these are the nodes that have one edge connected to it, and this is the nodes that have this, well, you have one node that has a degree of 6. And this plot below is going to plot that degree distribution on a log-log plot. So let's let this thing run, and this is really sort of a fun video because you can see these nodes being added and drawing new connections. And I want you to notice 2 things. Let me stop it for a second. Notice 2 things. First is there's some nodes that are way more connected to others, and that's captured in this degree distribution. So there's a lot of nodes that only have 1, and then there's a handful of nodes, including one that has 23. Now I can resize the nodes by the number of connections, and that gives you another way to see that this degree distribution is really skewed. So there's some nodes with very low degree, and there's some with a lot. So if I let this run even further, what you see is that degree distribution stays skewed. Like there's some nodes that have lots and lots of connections, and then others that have very, very few. So this preferential attachment rule results in this very skewed degree distribution, which is interesting. Now we saw that happen once, but just to prove it happens every time, let's run it again, and I'll put the resize node button on, and again you see the exact same sort of degree distribution showing up where subnodes are highly connected, others are less connected, but we're getting a very different network. So one of the interesting things is the distributional properties of the network stay the same, even though the exact network you're going to get is going to differ a little bit depending on how the process played out. Well, guess what? That means it's path dependent. So the exact network you're going to get is going to be path dependent. The equilibrium distribution of degrees is actually not going to be path dependent. You're almost always going to get the exact same degree distribution. But the network you get is going to depend a lot on the particular history. So we get sort of path dependent outcomes, but we don't have a path dependent equilibrium in terms of the degree distribution. That we know just from this process. At least we figured it out. You know, physicists and network theorists have figured out that you're always going to get this degree distribution. And this is the way to think of it. What you get is your long-tailed degree distribution. So what that means is there's a whole bunch of nodes that have a degree of 1, and then there's a handful of nodes that have a large degree. And so this is the probability that you have 1 degree, and here's the probability you have a large degree, and this is what that preferential attachment rule gives you, this sort of long tail. This is something that's called a long-tailed distribution. And this distribution is always going to occur when you have a preferential attachment rule. Now, which nodes end up being large degree and which ones don't, that ends up being somewhat path dependent. But the distribution itself is not. You get these long tails. And what that means is there's a big skew. Some sites have lots of, if you look at the internet or the World Wide Web, some sites have lots of links. Other sites have very, very few links. All right, so that's some sense of the logic of networks. If you just have random connections, then you get this interesting tipping point phenomenon. If you have a small world network, then as people have more random friends, you get a lot less clustering, but you get shorter social distance between people. And finally, if we have a preferential attachment rule, what we end up getting is we get this long-tailed degree distribution where most nodes have very, very low degree, but a handful of nodes have a really, really high degree. All right, thanks.